All right, let's dive right into this explainer. Today we're unpacking some truly groundbreaking research that asks a fundamental question about our modern infrastructure. How exactly do we keep the lights on when things go wrong? We are going to explore how the future of green energy distribution might just be a power grid equipped with its very own digital immune system. It's a completely novel architecture, and honestly, it's going to change how we think about electricity.
Here is our roadmap for today. We'll start with the power grid problem, move into the self-healing solution, break down how multi-agent systems work, test the digital grid, and finally, look at the physical hardware reality.
To kick things off, I want you to imagine a world where a massive lightning strike or maybe a downed tree taking out a power line doesn't mean sitting in the dark waiting for a repair truck. What if, instead, it triggers a smart system that literally heals itself in a matter of milliseconds? Now, that sounds like science fiction, right? But this is exactly what researchers are building today.
Section 1. The power grid problem. Centralized versus smart.
So to really appreciate the cure, we first have to understand the disease that's affecting our modern electrical infrastructure. For decades, we relied heavily on traditional centralized electrical grids. They were highly regulated, super rigid, and basically just pushed power in one direction. But today, we're moving toward modern smart grids. These are decentralized, way more consumer-friendly, and they're heavily integrated with renewable energy sources like wind and solar. But here's the catch. As we integrate all these decentralized sources, our power distribution networks are becoming incredibly complex. They are highly networked, and they have to handle real-time disruptions without breaking a sweat, which you can imagine makes them so much harder to manage when a fault actually occurs.
Moving on to Section 2, the self-healing solution, multi-agent systems.
Okay, so how do we actually protect a system that is this complex and decentralized? Well, the crucial point is that to prevent massive power outages, these smart grids need a mechanism to automatically predict, identify, and respond to issues. It's exactly like white blood cells isolating a wound in the human body. The absolute heroes of this story are what we call multi-agent systems, or MAS for short. You can think of a multi-agent system as a decentralized team of highly trained digital dispatchers. They're made up of these automated, embedded sensors and controls acting as totally independent agents, and they are constantly talking to each other just to monitor the grid's overall health. When a disruption, or a fault, hits the grid, these intelligent agents execute this brilliant three-step playbook known as FDIR. First up, they automatically detect the fault. Second, they isolate the damaged section. That's basically the quarantine phase. And third, they restore power by rerouting the electricity through alternative channels to keep the rest of the system totally alive. Fault detection, isolation, and restoration. FDIR.
Section 3. Multi-agent systems and how they actually work. Let's look under the hood. To prove this FDIR concept, researchers didn't just write a bunch of theory. They built a full-on digital matrix. Using MATLAB Simulink alongside the Java Agent Development Environment, which they conveniently call JADE, they created a totally simulated neighborhood. In this model, you've got generators, overcurrent relays, and circuit breakers all linked up. The digital agents gather real-time data from these relays to figure out exactly where a fault is located. Then, they issue very precise logic signals to the correct circuit breakers to isolate the damage.
And the way they communicate is fascinating. It all boils down to a strict, elegantly simple binary logic protocol. A 0 means a fault has occurred, which tells a specific circuit breaker that it needs to open and cut the power to quarantine the issue. Meanwhile, a 1 tells the backup systems and alternative routes to close their breakers, which safely restores power to the isolated loads. It's literally just a rapid-fire sequence of zeros and ones that saves an entire neighborhood from a blackout.
Section 4. Testing digital grids by simulating outages. To really push this system to the limit, the researchers scaled things up to a dynamic 9-bus active system. Think of this as a digital neighborhood map with 9 major electrical intersections. This environment features 11 distinct loads, which represent different neighborhoods or industrial centers, and 4 separate generators. In this environment, they simulated massive, symmetrical 3-phase faults at 6 different sites across the map, just to see if the agents could actually save the homes from going dark. And when you compare the outcomes over a 13-second simulation, it's night and day. Without the FDIR algorithm, when a fault hits, power just completely drops out for the connected loads. We're talking massive, sustained outages. But with the FDIR agents active, the system incredibly quickly reroutes the power. The gaps are filled in almost immediately because the agents dynamically shift power from unaffected generators straight to the endangered loads.
If we focus in on one specific household connection during a fault, they designated this one as load 3. The results are absolutely staggering. The voltage drops to 0, yeah, but only for a tiny 0.1 second relay delay, literally the blink of an eye. The alternative generators instantly step in, perfectly directed by the agents, and the voltage is completely restored. The homeowner wouldn't even have time to reach for a flashlight.
Section 5. The hardware reality and building the physical prototype.
Because a digital simulation is only half the battle, right? The researchers knew they had to build a physical prototype to prove this could actually function in the real world. So they grounded their digital theory using very accessible, off-the-shelf components. They simulated household loads using standard 60-watt incandescent lamps. For the main brain of the operation, they set up a Raspberry Pi to act as the central server. This server communicated with Arduino microcontrollers acting as intermediaries to read sensor data, while ESP8266 Wi-Fi modules were used as clients to physically control the circuit breakers. And to detect the faults, they used CT1270 current transformers.
So in this physical prototype, which featured 6 loads, 3 generators, and 6 potential fault locations, those current transformers are acting exactly like a biological nervous system. They're constantly monitoring the lines, just waiting to detect dangerous current spikes. The moment a fault is simulated, they instantly sense the danger and fire that data off so the Raspberry Pi can orchestrate the cure.
The whole operation is tied together seamlessly using wireless MQTT communication. If you don't know it, it's a super lightweight messaging protocol that's absolutely perfect for the Internet of Things. The sensors detect the fault, the Arduino passes it up to the Raspberry Pi, and then the Pi sends wireless commands right to the ESP8266 modules to trigger the physical relays. In their physical tests, this system successfully isolated faults, shrinking what would have been a widespread, catastrophic blackout down to just a single, unavoidable affected load. The hardware completely validated the digital theory. It proved that this self-healing algorithm isn't just effective, it's completely viable for the real world. Exploring this research leaves us with a deeply provocative thought. We are aggressively transitioning to a highly decentralized green energy future, combining solar, wind, and countless localized microgrids. As our power grids grow ever more complex and, frankly, increasingly vital to our survival, self-healing technology isn't just an interesting academic convenience anymore. It might just be the immune system our modern infrastructure absolutely demands to survive. Thanks for joining me on this explainer, and I really hope this sparked your curiosity about the invisible, intelligent networks powering our world.